Good morning and welcome to the first seminar of the 24-25 academic year of the Repsol Foundation Chair of Energy Transition, held at the University Rovira Virgili and organized together with CO2 Value Europe. It's a pleasure for the URB professors involved in this chair to contribute to the organization of this event about CO2 utilization, a transformation potential into products of industrial interest. Before we start, let me briefly introduce myself. My name is Ana Maria Mas de Bultó. I'm professor at the Department of Inorganic and Physical Chemistry at the University of Rovira Virgili, located in Tarragona, Spain, 100 kilometers south of Barcelona. URB is a dynamic university placed in a strategic location, given the fact that Tarragona holds one of the biggest petrochemical hubs in South Europe. Last year, we embarked in a collaboration with the Repsol Foundation to create the chair on energy transition at URB, an endeavor that is led by Professor Felix Lluvell. The chair focuses on the study of CO2 capture, use, and the regulations related to this subject, with 3 specific lines of work, each led by a professor of the URB. These lines of work are, first, the capture and negative emission technologies, is led by Professor Lluvell, with a major focus on carbon removal through negative emission technologies, which aim to remove CO2 directly from the atmosphere, often through processes like afforestation, bioenergy with carbon capture and storage, or direct air capture. The second line, the uses of CO2, is led by myself and explores a variety of possibilities trying to convert a residue into an added value product. CO2 can serve as a valuable feedstock for various industries, being converted into chemicals and fuels through processes like carbon capture and utilization. The third line is about CO2 regulation and standards. It's led by Professor Estela Ribas and focuses on regulatory frameworks, policies, and strategies implemented at local, national, and international levels to mitigate CO2 emissions and combat climate change. In the chair, we analyze aspects about the topics with the aim to contribute to the dissemination of them at different levels. Overall, the goal is to increase the awareness of the society about the multiple aspects involved in the decarbonization technologies. In this session today, after the welcome of Repsol Foundation Ruth Yerga, we will have a keynote by Anastasios Perimenis, Secretary General of CO2 Value Europe, and a panel of experts that will count with the contribution of Diana Cano, Head of Renewable Fuels Project at Repsol, Francisco Pelayo Garcia, Group Leader at the Institute of Photonic Science, Walter Leiner, Director at the Max Planck Institute of Chemical Energy Conversion, and Peter Bunig, Director of Sustainability and Technology at OCO Technology. And then we'll have questions and answers and a closing remarks. But before we start the first keynote, I will provide some context. The European Union has set out a plan to eliminate by 2050 net greenhouse gas emission, an important part of them, carbon dioxide, to achieve a climate neutral society. These actions will generate important stocks of CO2 that can be reused by means of carbon capture and utilization, CCU. They can be used as a raw material for obtaining carbon-containing products. However, CO2 utilization technologies still face challenges such as the development of more efficient and economical viable conversion and purification technologies, as well as the stability and regeneration of the catalysts and absorbents used for these processes. Today's webinar focuses on the decarbonization aspect, that is to answer questions such as, is CO2 a waste that we should get rid of? Or can we obtain useful products from it? Can we obtain from CO2 the products that come from oil? Can we long-term fix it into products that can be used somehow? We are aware that this subject has a lot of interest, and the proof is that we have today near 1,200 registered people. So we hope that we will be able to provide some insight in it with the view of the different experts participating in this webinar. So now I will introduce Rovira from the Repsol Foundation's network of university chairs. Please, Ruth, the floor is yours.
Thank you very much, Anna. Good morning and very welcome to all of you who are joining us live today. This webinar is organized by Repsol Foundation in collaboration with the University of Rovira Virgili in Spain. We are pleased to know that almost 1,200 people have registered for this event. Before we start, I would like to express my gratitude to the university and all our dissemination partners for their collaboration in this event, where we will discuss the importance of carbon utilization and its role in industrial decarbonization. I would also like to thank the speakers who have accepted our invitation to share their knowledge and experience in this field with us today. Last but not least, many thanks to the audience attending this webinar, which is part of the programming we offer through our open room, which is Repsol Foundation's free digital platform on energy transition. Some of these events are promoted by Repsol Foundation's network of university chairs, including today's event. The mission of this network is to analyze critical issues for the future of our planet regarding energy transition with the ultimate aim of transferring knowledge and spreading awareness to society through rigorous debate. This is the case of Rovira Virgili University Chair, which was established in 2023, focusing on three main topics: CO2 capture, CO2 use, and regulation. Today, more than ever, energy and energy transition are prominent in public debate and societal concerns. This involves everyone, public and private sectors, as well as consumers. Many issues need to be considered to form an informed and neutral opinion on the energy transition to make it a reality. Thus, it is crucial that prestigious universities with renowned experts, such as the University of Rovira Virgili, work on engaging the wider society on this topic. In 2025, we have planned over 60 initiatives in Open Room Digital Community, including events, webinars, courses, and conferences, where we will address multiple current and interesting topics related to the energy transition. Today, we will count on a comprehensive overview of CO2 utilization technology and projects, their talents and opportunities. Carbon utilization is part of the solution in the fight against climate change. It offers a way to reduce emissions, create valuable products, and potentially drive innovation in green technologies, all important steps toward addressing climate change. CO2 utilization is important for the European Union's decarbonization goals because it provides a practical way to reduce emissions across sectors, supporting the circular economy, enabling carbon neutrality in industry, all while driving economic growth and job creation. Without further delay, I will hand the floor back to Anna. I hope you all enjoy this event, and once again, thank you for your participation.
Thank you, Ruth, for your words. And now it's my pleasure to introduce the first speaker of the day, Anastasios Perimenis. He is the Secretary General of CO2 Value Europe. Anastasios holds engineering degrees from Greece, Germany, and Belgium. Over the last 14 years, he has conducted fundamental and applied research in a series of subjects linked to the development of sustainable and circular economy. Since 2020, he is the Secretary General of CO2 Value Europe, leading the operational work of the Association for the recognition of CCU as an essential solution towards a climate neutral and carbon circular economy. Please, Anastasios Perimenis, the floor is yours.
Thank you very much, Ana Maria. Thank you all for joining today. It's a pleasure to be here, and it's thank you to the organizers for having us here. My name is Anastasios from CO2 Value Europe, and I would like to give you an overview of the CCU context at the European level today. Just a small confirmation that you can see my screen so that I'm sure that what I'm showing is visible.
Yes, we can see it.
Yes, perfect. Okay, first starting a little bit about who we are, who is CO2 Value Europe. It is a European association. We were formed at the end of 2017, and we are dedicated to CCU, so to carbon capture and utilization. And we bring together stakeholders from the entire value chain and also across industries, which is what is rather non-typical about an association, is that we integrate actors from different industrial settings, because for all of them, industrial carbon management is relevant and important. This is an overview of our membership base. You can see that it is pretty equally distributed. So around 1/3 large companies looking for solutions, around 1/3 research and technology organization researching on CCU pathways, and another third, a little bit more, of SMEs that are usually the technology providers for converting, capturing and converting carbon into useful products. We have 4 basic priorities and 4 areas of work. The first one is to gather and provide scientific and technical knowledge about the developments of CCU technologies and mutualize this information, be it maturity of technologies, which are the technologies that are out there, who's behind them, what are the projects that are ongoing or upcoming, all this type of information. We also have a database with CCU projects that are ongoing or upcoming that you will see also later. So that's one part of what we're doing. A second part is to make sure that we have a consistent and supportive regulatory framework for the development of CCU. And I will give a couple of examples later on. The third one is to support stakeholders and our members and non-members also, for that matter, to come together, to network, to develop contacts and foster this collaboration to see low TRL, innovative, but also commercial scale projects come into life. And the fourth thing is awareness raising, stakeholder engagement and communication about the subject. Not everybody knows what CCU is, and there are also a lot of misconceptions about CCU, CCS, CCUS, CDR. All those terms sometimes are being used in a confusing manner. So we communicate about the subject, about us, about what our members are doing on that, so that we can raise awareness about the subject and its merits. So what is CCU? I won't go into much detail on that, but basically it's a circular process where carbon dioxide is captured and this carbon can be used in a product. We follow the definition of the IPCC, and this conversion can take place under many technologies. It could be thermochemical, could be electrochemical, biological, and you have a wide spectrum of products that can be produced from those technologies. And at the end of life, the CO2 will either be permanently bound, or it will come out again and it can be captured and continue this circle again. So the basic reasons why CCU is important, among others, but importantly, these are arrays of of processes that can lead to emission reductions, that can lead to net zero processes and pathways, and can even lead to carbon removal, so not negative emission. And that depends on what kind of product you will use and where is your CO2 coming from. Importantly, and something that is often neglected in the discussion, is that CCU is not only a climate mitigation option. It's not only there to treat emissions, but it's also there to bring an alternative carbon feedstock into the production system. So we don't have a lot of possibilities to substitute fossil carbon. So there's biomass with its physical constraints. You can recycle a lot, chemical and mechanical recycling. And then you have CO2, which is a scalable alternative carbon source. And that brings more circularity into the production system. If I can give an example, focusing on the fuel part, you would have an initial CO2 emitter, let's say a cement factory, and that would emit CO2, and then you would have your transport sector that will consume also fossil resources and would emit also CO2. If you want to claim emission reductions, then you can take the CO2 from the cement factory, for example, convert it into a fuel, and thereby substitute fossil fuel for the transport sector. And by this substitution, you can claim emission reductions. And if you keep on recapturing this CO2 after its emission and rebringing it into the system, reproducing CCU fuels or e-fuels, as we call them, and use them in a continuous loop into the system, then you are leading to net zero pathways. Or if you are taking this CO2 from the atmosphere, from the air, or from biogenic CO2, and you produce e-fuel, then you're also contributing to net zero pathways. So these are some examples of the importance of CCU. And recently, in February last year, we have tried to quantify this contribution of CCU towards climate neutrality, towards net zero by 2050. And to answer to some questions like how much CO2 are we going to need to capture, how much of it will go to use, how much will go to storage, which economic sectors will see most of the reductions, how much electricity will we need to do that, where is the CO2 coming from. So all these are in the report that we have published last year. If I did my work correctly, then the barcode should function normally. But as a main message from this report, and here it's a simplified illustration so that it is more visible, is that looking at the graph from left to right, we are the blue column were the emissions of 2019 as a reference point, and under stated policies, we would be able to reduce 1/3 of those emissions by 2050. And that's the second column, which means that we need around 2/3 of further effort. And we modeled this further effort, and we developed scenarios of this further effort where CCU is a part. And we saw that another 1/3 of what we need would come from societal choices that we have to do as a society overall to reach climate neutrality. And the last part, the last 1/3, would come from technological choices, from the technological effort that can be take place. And of that part of the technological effort, CCU would correspond to 20%. So overall, around 8% of the emission reductions that we need until climate neutrality would come from CCU by 2050. And this is something that is happening already. So it's not something of the future. Here we see a list from our database, a list of projects that are expected to become operational by 2030. So in 5 years' time from in different areas, and the list is not exhaustive, but in different areas at different capacities for different products. And that shows that there is a momentum of creating projects at industrial scale. And we need to foster and to keep this momentum going, because these products will substitute the conventional fossil-related products and will bring more circularity into our production systems. And to make these projects happen, like every other innovative clean tech solution, it needs support. It needs funding and financing support. Here I'm showing 2 examples where CCU is relevant and has been supported. The Innovation Fund, which is probably the largest fund, clean tech fund, also globally, I would say, with around 40 billion euros financed from the emission trading scheme until 2030. And so far, at least 14 projects with a CCU element were supported during the first 3 calls. And this is an instrument that is evolving. It includes different scales. It started with large and small scale. Now it also has a medium scale. It supports different financing instruments like hydrogen auction for the last call, and this one, the one of this year. It has sector-specific support, for example, for the marine industry. So it's and CCU is eligible, and we encourage our members and our stakeholders to profit from this. We also have Horizon Europe, the successor of Horizon 2020, which is the main R&D framework program from the Commission. In the first years, as of 2021, we had around 44 CCU-related topics, and around 35. It's an approximate number because not all of the topics have been concluded, with around 370 million that has been supporting CCU projects. And within it, also keep in mind the Clean Energy Transition Partnership with a specific module for CCU that signifies the support of the member states, because it's member state resources that come into this partnership. And so we talked projects, we talked funding. Let's talk a little bit about policy without going into the details. So I'm not gonna drive you crazy by going into the details of each and every one of the instruments. I call this the headache slide because it shows how complex the policy framework is in Europe. We tend to over-regulate stuff. With the Green Deal, you probably have heard about the Fit for 55 package, the package that will make us fit to reach our goals of 55% emission reductions, leading us to climate neutrality by 2050, and the 55% is by 2030. You see many different instruments, some more, some less, but they are all relevant for CCU, and they will all evolve, influence how CCU is evolving and how much we will see it deploy at large scale in Europe. Some of them are new, some of them are older that have been revised to make us more fit. You have probably heard about the emission trading scheme. You have probably heard about the Renewable Energy Directive. Something to come in the next weeks with the new Commission is the Clean Industrial Deal, or the Industrial Decarbonization Accelerator Act, and some of these legal instruments are binding. Some are more of a communication. In the EU jargon is more like an aspirational strategy. like the industrial carbon management, which is quite important as we speak now. So all of those instruments are relevant. Some are more generic about industrial carbon overall, and some are more topical about a specific sector, aviation, maritime. In the next slide, we can see a couple of examples. This is with the view of you having this presentation, and you can look at it at your ease afterwards. But if you look at the ETS, the emission trading scheme revision, where basically the ETS is you have to pay for allowances to be able to emit, and it has been recently recognized with the revision of the ETS that when you bind this CO2 in a permanent way into a product through mineralization, for example, you don't have to surrender your allowances because the CO2 is not coming into the atmosphere again. As we speak, there is a discussion of how you can incorporate those uses and application of CCU that are not of permanent binding, like fuels or chemicals, where the CO2 is eventually at the end of life coming out again, but it's substituted a fossil conventional counter product. And this is a discussion that is happening now. If you look at Refuel EU Aviation, the fourth in the list, for example, there you have quotas for sustainable aviation fuels. And by quotas, we mean that the fuel the fuel supplier and the airlines are obliged to use X% of fuel in aviation, of sustainable aviation fuel. And there is a subcategory for synthetic aviation fuel, which is basically CCU fuels. And these type of quotas, they drive the market because there is an obligation that will count towards the goals of the Commission. So it is a signal that this product will be taken off by the end users. So it's a signal to the investor, yes, go on with the production of that fuel. You have the industrial carbon management strategy, which is a communication and a strategy that explains how industrial carbon management can be treated in the next years, mentioning around 200 megatons of CO2 to be reused by 2050. And we are also participating there, chairing a working group on CCU. To sum it up, because I think I have a couple of minutes left. So what we have calculated with our work that I mentioned before, and it's not very far from what the Commission says in its impact assessment for the 2040 targets and in the industrial carbon management strategy, is that CCU can represent around 45% of the carbon that we will need to capture in Europe. That will be around 450 megatons. And that can be used for the production of fuels, chemicals, and materials to defossilize various economic sectors in Europe. We have several projects, as we have shown, that are able to become operational, but they need a policy framework that is consistent, that is pragmatic, so considerate of the industrial realities, and not, especially at the beginning, not overly strict on how you can access your renewable electricity or what kind of CO2 you will be able to use and until when. So that is very important for projects that are ongoing now, and we have also seen some projects being stopped because of this regulatory framework difficulties. We have seen also that not all CCU strands have received equal support. So for the moment, for example, incentives in the CCU chemical part are absent. An example, if you use virgin fossil carbon for the production of the chemical, you are not obliged under the ETS to surrender to pay any allowances. But if you use captured carbon to produce the same chemicals, this captured carbon has already been upstream accounted for. So it's a clear disadvantage of captured carbon compared to virgin fossil carbon. So we need the regulatory support. We need also the funding and financing support, because we, apart from regulations, we are now at the stage where we need to actually implement all the goals that we have and create projects and see those projects reach industrial maturity and industrially relevant scales. And this support will be necessary to cover the competitiveness gap with the conventional value chains. That is always the case when innovative clean tech solutions come into play. Appeal to engage to all of you that are listening, to engage in platforms like the Industrial Carbon Management Forum to further drive those developments. Thank you. That was my last slide. And follow us on our social media. Check our website. Engage with us. If you are interested in what we're doing, talk to us and work with us to drive this value chain further. We have a newsletter, we have our social media that you can look at, our website with all our publications. So yeah, engage with us, and I hope you enjoy this webinar.
Thank you, Anastasios, for this overview of the projects of CCU and the activities of CO2 Value Europe. But let's move now to the panel of experts. But before we start, I will provide you some context about related with the role of research in CO2 transformation to highlight some key aspects that are currently the focus of investigation. It is clear why we are talking about CO2 transformation, but the question is, how are we going to do it efficiently? So first issue is that CO2 is a very stable molecule. Carbon is at its most stable oxidation state, and it is very inert. Nevertheless, it can act as an acid which reacts with alkalis, and this is the basis of the CO2 capture and mineralization, being transformed into carbonates that retain it for a long term to avoid its return to the atmosphere. Apart from that, and in spite of its inertia, it contains some active points. Then it can act as an electron acceptor at the carbon and as an electron donor at the oxygens. And then the molecule can be activated through using catalysts through these active points in different ways. Then the catalyst development at this point is crucial for CO2 transformation. And the capture technologies implemented so far are mostly related in the acid-base character, in this acid-base reaction mostly with alkanol amines. But this process has some drawbacks due to the need of energy to separate the CO2. Then, among other issues, then new processes to avoid the issues have to be developed, and the use of porous adsorbents for physical and chemical absorption is one of these possibilities, other possibilities, and materials such as zeolites, porous carbon, and more recently metal organic frameworks have shown high absorption of CO2 capacity. Metal MOFs are metal-containing porous polymers consisting of metal coordinated to ligands, which are interconnected between them to form one, 2 or 3 dimensional structures leaving pores where CO2 can be absorbed. These materials are not only applied to capture, but since they may contain active metal center, which is the case of this magnesium example here, They are also explored to capture and reactivity connected technologies, the so-called reactive carbon capture. But the transformation to carbonate-based materials can be a way to reuse CO2, not only to get rid of it, but to prepare useful materials such as aggregate for building materials. And when CO2 comes from direct air capture, for example, it could contribute to negative emissions. A joint project of Repsol, Petronor, and Ausio has developed this construction and will be presented by Peter Guni. But another example of products obtained from CO2 are organic carbonates, polycarbonates, or cyclic carbonates. And they are obtained by reaction of CO2 with epoxides and have multiple applications as a solvents, for example, as a solvents for electrolytes in batteries, as a polymers. One interesting line of research in this area focuses on discover sustainable epoxides derived from the natural sources. One example, prepare polycarbonate from limonene derivative. This was developed by Clyde and co-workers, and using a very active aluminum catalyst, and the polycarbonate obtained can be derivatized to obtain products, materials, polymers that can be an alternative to those based on oil derivatives or to those based on bisphenol A. Another example can be found in the field of the non-isocyanate polyurethanes, and was developed in our group in collaboration with Professor Galia from our university and Professor Agnew from Tetuan University. In this case, a derivative from castor oil was transformed to oxide, and using a catalyst obtained from vegetal waste, it was transformed by reaction with CO2 with 2A cyclic carbonate that was then reacted. It reacted readily with diamine to form this polyurethane that can be used as a polymer. So these are a couple of examples from alternatives that are being developing. And regarding other products such as methanol, methane, fuels, or carbon monoxide, they can be obtained from reduction of CO2 and using hydrogen, and they can be used as a fuels directly. Methanol or methane, they have the advantage that the emissions of CO2 are less important, but also they can be obtained they can be used as a chemical intermediates for products. Examples of, for example, the production of methanol by the ICA process is an established method, an established process using aluminium, zinc, and copper-based catalysts. And now in this area, the research is focusing on the use of multifunctional catalysts that can transform CO2 to fuels directly with the same catalyst. And another important aspect is the transformation of CO2 to what they call e-fuels. And for that, first of all, the first reaction is to convert CO2 by reaction with hydrogen to CO, mixture of CO and hydrogen, syngas, and then by the Fischer-Tropsch reaction, these materials, this syngas, can be converted to the e-fuels, and this topic will be explained and presented by Diana Cano. So then the challenge now is to use renewable energy to produce these reduction products. Electro or photochemical reduction can be done using catalysts, and Francisco Pelayo will give us an insight in this subject. But let me show you one example of an electroreduction of CO2 to CO and hydrogen. and that has been developed by a joint effort of Siemens and Evonik in the project Reticus. And this is the first electrolyzer of CO2. And in this case, from the electrolyzer, a syngas mixture of CO and hydrogen is obtained, and this CO hydrogen is then feeding then a bioreactor, which is full with microorganisms, which are able to transform CO and hydrogen to butanol and hexanol. So that is a proof of the possibilities of the electrochemical transformation of CO2. And in this case, the key point is to use renewable energy to reduce the footprint, the CO2 footprint. Regarding the photo reduction, the use of light for the to assist the CO2 reduction, there is one line of research in which non-noble metal-based catalysts are developed. In our group, we developed a family of iron complexes. We were able to produce a mixture of CO and hydrogen, syngas. The conversion were still not optimized, but in this case, we need to use a ruthenium-based photosensitizer. So still the dependence with noble metals, but recently, and there are other examples in the literature, there is, in this example shown here, a cobalt complex with a porphyrin is able to selectively transform CO2 in CO using an organic dye as a photosensitizer. So the research in the photochemical reduction of CO2 and to develop new strategies is quite important for the efficient transformation using light. And then what is a real challenge and many efforts in the scientific community is to transform CO2 to C2 compounds, that is, compounds that have more than one carbon, C2 or more than one carbon, like ethylene, ethanol, and higher hydrocarbons. And this still the problem is the low activities and selectivities. In this field, the electrochemical reduction of CO2 to C2 or higher carbon products is highly desirable, but still very challenging. But there are some examples in which carbon-carbon couple is obtained, is produced. In this case, in aqueous electrolytes, there are some examples. The mechanism of this transformation involves the first one electroreduction of CO2 to form active intermediates that then, with one carbon, that then needs to couple, and this coupling can follow multiple mechanisms, and that's why the selectivity are still poor. But there are some examples with metal-based catalysts, for example, with iron, cobalt, nickel, copper, and zinc, etc., that have been applied to obtain mostly C2 compounds. And the strategies is important. The strategies of the tuning of the design of the catalyst. For example, they has been using nanostructures. They has been tuning the defects of this structure, or the support is important. They have been using alloys with different metals to promote the reduction and the coupling, and also single atom catalysts. So as a conclusion, there are multiple scientific and technological challenges to be faced for develop the potential of CO2 transformation. And just a last idea, there is no research without the support of society that allows or fosters the investment coming from the public or private resources. So the chair is very much involved in dissemination of the decarbonization subject through local media and participating in side events. And also, in that sense, the University of Rovira Virgili is organizing a Master on Industrial Society Decarbonization Management. We will hopefully start next academic year and will cover the multidisciplinarity complexity of decarbonization. Thanks for your attention, and let's go now to the next speaker. Let me introduce and start with the panel's expert. Let me introduce Diana Cano. Diana Cano is Renewable Fuels Project Manager at Repsol. She's a chemical engineering and has been working at Repsol for 24 years. After working in the technology department, she switched to the business line, where she mainly focused on issues related to decarbonization of the refining industry. Currently, she is dedicated to renewable fuels project, biofuels, and especially synthetic fuels that Repsol is performing in its own assets and also with partners and other locations. Please, Diana Caro, the floor is yours.
Hello, good morning. First of all, I would like to thank the session. In this webinar, share with all if and what we are doing. Of my presentation in this case, I will. Secondly, I will talk about e-fuels, definition, pathways, how they are covered by European regulations. Finally, I will explain a project that Repsol is currently in a partnership with Saudi Aramco and the challenges involved in scaling it. Repsol is a global multi-energy Spanish company with a vocation in the energy transition. Repsol was the first company in the industry to announce its net zero emissions by 2050. But how? Repsol defends technological neutrality. To achieve this goal, we adapt the current model of refineries and petrochemical processes to low carbon plants. Replace the use of conventional crude oil, electricity, natural gas, with renewable resources, waste and biogas. Conventional products like fuels and chemicals will be replaced by renewable products like recycled plastics, hydrogen, and renewable fuels, both biofuels and synthetic. Okay, then let's start to explain what are the fuels and the role that they will play in the decarbonization of transport. E-fuel is a term used to describe synthetic hydrocarbons resulting from the combination of renewable hydrogen and CO2 coming from a concentrated source or directly from the air. E-fuels are also named as RFNBO, renewable fuels of non-biological origin. You can also name as power to liquid, synthetic blending components, etc. Let's go into the detail of the production pathways. E-fuel production starts with the renewable hydrogen production. This is done by an electrolysis process that breaks down water into its component, hydrogen and oxygen. Renewable electricity is required. The second feedstock needed is CO2 and captured either directly from the air or from an industrial source, which can be biogenic or fossil fuel. The regulation establishes that non-sustainable CO2 will be banned from 2041. Basically, that means that in the future, if they will have to be produced by biogenic CO2, and this is an important challenge. In the first process step, the hydrogen is combined with CO2 under pressure and temperature using catalysts, either directly through the methanol route or with syngas through the Fischer-Tropsch route pathway. In the methanol route, a second step is needed to transform the methanol, the alcohol, into paraffins in different steps to produce the final products, e-gasoline and e-kerosene. In the other route, in the Fischer-Tropsch route, the hydrogen reacts with CO2 and forms the syngas, the carbon monoxide and hydrogen, and then it will react in the Fischer-Tropsch, that is a well-known catalytic process in which the syngas is converted into liquid hydrocarbons or synthetic crude. This synthetic crude is upgraded until the final product. The context, how is the regulation in Europe? E-fuels are not specifically defined by regulation, but they are included in the RFNBO definition. The European Commission is reviewing to recognize light-duty vehicles that are fueled exclusively with e-fuels. Heavy-duty regulation is under discussion and will be impacted by the other one, by the light-duty vehicles regulation. Along the Fit for 55 package, there are specific mandates for e-fuels, for RFNBOs in all transport modes. We have objectives or different targets in the Refuel EU Aviation, in the Fuel EU Maritime, and also in the Renewable Energy Directive, RED 3, for all transport modes. So clarity in regulation is very important in order to be able to carry out investments for the private and public sector. This graph shows the CO2 emissions from road transport in the EU and the reduction that we can expect up to 2050, depending on the technology. Business as usual provides up to 15% new types of engines, as the electric ones provides up to 45%. The improvement in efficiency provides another 9%, and renewable fuels up to 31%. Renewable fuels can be biofuels, but and e-fuels. The problem with biofuels is that are limited by the availability of sustainable feedstock, and the contribution of e-fuels are essential. The message here is that the CO2 reduction demands a mix of technologies, and renewable fuels or low carbon fuels play a significant role. If we talk about the carbon balance in e-fuels, we see here that in the production process, the CO2 that is captured to produce the e-fuel is the same, is equivalent to the one that is emitted to the atmosphere. That is what we call net zero CO2 emissions in use. We are talking about an exhaust type. If we talk about the well-to-wheel balance, if we compare to the fossil, the conventional fuels, we have a very important CO2 footprint reduction with e-fuels. Then, to summarize, why e-fuels? Because they are net zero emissions, because they are compatible with existing infrastructure and fleet. They are a solution for a wide range of sectors, aviation, road, and marine. They are unlimited, practically, because we have available CO2, renewable electricity, and water, that finally are the raw materials. They are an alternative for non-fuel products like lubricants, chemical industry, or waxes, and they are a renewable energy vector. Let's go into the explanation of the project that Repsol is currently developing. The project consists of a first-of-a-kind demonstration plant that will use capture CO2 and renewable hydrogen as raw material. The objective is to demonstrate technical and economical feasibility of the synthetic fuel fuel production through Fischer-Tropsch pathway, integrating and operating the technologies that we are going to use to produce the e-fuels. If we go into the project details, the demonstration plant will be located in Bilbao. The operational date, the startup during 2026. The capacity of production is around 2,000 tons per year of e-fuels. The CO2 avoidance is around 7,000 tons per year. The demonstration plant will use green hydrogen from a 10 megawatt electrolyzer that will be located in the same place. The objective, as I explained before, is to demonstrate the technical and economical feasibility of the e-fuels production through Fischer-Tropsch. Some key insights of the project. We will produce drop-in fuels that can be blended in existing engines. We will demonstrate the whole value chain of producing synthetic fuels, and we will perform real fleet tests in market with clients and partners. So the project consists of a demo plant composed of 3 different units: reverse water gas shift to produce the syngas, the Fischer-Tropsch process to produce the synthetic crude, and finally the upgrading unit that will produce the final products: e-naphtha, e-kerosene, and e-diesel. We have a technological plan to de-risk the technology. About the partnerships for e-fuels production. The partners, the investors, are Saudi Aramco and Repsol, 50% each. Petronor is a part important of the project as it provides integration with the refinery that is very close to the demonstration plant. We have 2 technology partners, Johnson Matthey and Access. And the last but not the least, we have a partnership with Basque Hydrogen, that is the company that has been created to build the 10 megawatt electrolyzer. And the shareholders are Alba, that is an affiliate of Repsol Petronor, Enagas Renovable, and the Basque Energy Agency. The demonstration plant will be located or is being built currently in the Bilbao's harbor, and is fully integrated with Petronor refinery that is a few kilometers far away from the demonstration plant. We can see here the location of the demonstration plant in the harbor facilities. This is the plot of the plant and the refinery here. They are integrated because the refinery will supply the CO2. The CO2 is currently captured in an industrial plant in the refinery. We have future plans to replace this CO2 with DAC, with CO2 captured from the air. And the hydrogen from the demo will be connected with the refinery with a reversible line that can provide hydrogen to the demo in the case of any electrolyzer failure. The next step will be the scaling up of e-fuel production. We need to face some challenges, and on the other hand, we have new opportunities. Regarding the challenges, we have business challenges. The first one, and very important, is the cost and investment necessary for producing fuels is very important. Also, we have the regulatory framework is very demanding. We have obligation of synthetic fuel in transport sector. We have some restrictions for the CO2 source origin. We need hydrogen. It's complicated, the greenhouse gas avoidance calculation. We need to integrate with current assets. We need to have the products in the specification and with the certification. It's another challenge. Regarding the technology challenge, we need to scale up pilot and demo scale technology that are in low tier L, like reverse water gas shift, electrolysis, some electrolysis technologies, and the DAC. For that, we need to validate and integrate the whole processes in an economical and steady operation. We need to optimize the operation, and we need to improve the energy efficiency of the project. The engineering challenges are regarding the hydrogen infrastructure. We need to scale up the electrolyzer and the grid connection, and we need to cope with the availability of eligible CO2 at scale. Finally, the direct opportunities that we are facing are the Refuel Aviation, the Refuel EU legislation sets a minimum synthetic fuel in kerosene blended fuel from 2030 up to 2050. This is a clear mandate that increases over time. It's an opportunity. Also, this production pathway produce high quality streams with a high energy density, and it increases the flexibility for final products. We have a potential opportunity to integrate this new process in a refinery by reusing or retrofitting existing process units. We can accelerate the transport decarbonization because e-fuels are fully compatible with existing vehicles and fueling infrastructure. So to summarize, if we want to achieve net zero emissions in the future, we need to combine different technologies. Synthetic fuels are renewable fuels that will play an important role in sectors that are difficult to electrify, like aviation and maritime. They also have the advantage to be able to accelerate transport decarbonization because they are fully compatible with existing infrastructure. The challenge ahead is technology development with funding, financial, institutional, and social support to reduce the costs of this pathway. Thank you very much.
Thank you, Diana Caro, for sharing with us this project of Repsol. Now, let's go now. We are like 6 minutes delayed. So now let's move now towards the next speaker, Francisco Pelayo Garcia. He is the group leader at the Institute of Photonic Science in Barcelona. Francisco is a professor and group leader. His research spans the design and engineering of materials and systems for applications in clean energy, and focuses on developing scalable and sustainable technologies to produce chemicals, including green hydrogen and hydrocarbons from carbon dioxide capture and conversion. Please, Francisco Pelayo, the floor is yours.
Thank you, Anna. Let me share my screen. And well, thank you. Well, again, for the introduction. I'll try to be brief so we cut down the 6-minute losses in time that we accumulate. Okay, so I don't know if you can see the screen. I like normally to start with this brief animation. I don't have time to explain in detail, but I think this is a beautiful animation from NASA showing biogenic sources of CO2 in green and anthropogenic sources of CO2 in orange-brown. And you could look into this here in more detail. But today, now I'll try to summarize and explain. Well, first explain in more detail what CO2 direct electrolysis is and how this falls within the overall portfolio of technologies for carbon capture and utilization. So thanks to Anastasios and Diana, I don't have to explain this slide very well, but let me just summarize. Here you have in the left different sources of carbon here, and you have sources of hydrogen here. So conventional high TRL carbon utilization that was presented so far mostly relies on reverse water gas shift and Fischer-Tropsch to make large hydrocarbons or through methanol. So methanol is like a building block for the petrochemical industry. So through the synthesis of methanol and methanol to olefins and others also to make this. So CO2 electrolysis offers a path to avoid the direct use of green hydrogen. So in this path, you need green hydrogen that's produced from water splitting. you can directly in CO2 electrolysis generate the local protons that you need and then make these chemicals in a more integrated fashion and hopefully offering a path to energy efficiency savings. So CO2 electrolysis is rather good already to make syngas, but one of the appeals of this technology is that you can directly make CO2 molecules that were mentioned before by Anna, such as ethylene and ethanol directly. So you can bypass a lot of these processes, and then these ethanol and ethylene can be coupled with existing processes in further downstream oligomerization or directly used as fuels in the case of ethanol. So I explain a bit more now about the core of this technology. So in direct CO2 electrolysis, you need a carbon source. So this could be from the atmosphere, like DAC, or this could be from single point emitters, like from steel factories or cement factories. You need water, of course, and you also need electricity. And one of the appeals of this technology is that as opposed to Fischer-Tropsch and others, this can be directly operated with electricity, so it doesn't need high temperatures or pressure. So it can be coupled with renewables in a convenient way. So you have an anode, and the idea is that you have to break down the CO2 molecules in CO2 molecule fragments, normally CO fragments first, and then you also have to break down the water in the smaller fragments, like OH groups, for example, and you need to couple these guys on top of the cathode, catalyst electrode. You also have an anode to close the reaction where you normally oxidize water, and a membrane that separates these processes. So in doing so, you have access to a wide range of carbon-based molecules, small carbon-based molecules. So from CO2, you can make syngas, which is the combination of CO and hydrogen. And this is a very powerful chemical to make lots of more sophisticated chemicals, but you can make many others, okay? And a good way of comparing them is like which one of these chemicals is more interesting. So in this plot here, you could see, well, the production and megatons per year and market size in $billion per year of these chemicals. And in this vertical axis, you could see the potential for evasion of CO2 per year in gigatons. And what we try to highlight here in different colors is in gray colors, you could see the abatements that would result in, displacing current processes. So, transforming the process, and in green, using direct CO2 from the atmosphere as a feedstock. So this is the potential. From this, of course, you have to subtract the emissions of your own process. So this is how much you can save in theory. So you can see here already ethylene as a very important chemical with large markets, large productions, but also large evasion potentials considering this, ethanol, methanol, of course, and CO and syngas, and eventually jet fuels as one of the largest markets for fuels. Now, my idea is to show a bit of the state of the art and where we are now compared to where we were like 10 years ago. So to do that, I'd like to introduce you some figures of merit. So the viability of this technology relies on getting some key performance indicators into the right place. So one important metric is the selectivity. You can make many different molecules, so it's important to be selective to the molecule that you like. And in electrochemistry, this is often referred to as Faraday efficiency. So how many of the electrons that you use go to the desired target reaction. From this, it's important then to consider the rates. How much product are you generating per unit of time? So this can be approximated by the partial current density. So it's the current density that you put into the system multiplied by the Faraday efficiency. So that tells you how much product you produce per time. Then you have energy efficiency. So you need to input some voltage here, and then you get a product that has some energy. So there is an energy efficiency of this process, as well as what is the operating lifetime. So these systems are not yet as stable as we would like them to be. So how many hours these systems can be reliable. So these metrics are connected to important techno-economic aspects such as OPEX and CAPEX costs. Mostly Faraday efficiency and energy efficiency relates to the OPEX. So how efficiently are you using your electrons? And this is very important because a large fraction of the cost comes from the use of energy. And CAPEX refers to what's your investment and how soon you can overcome the initial investment. So you need high currents and long operating lifetimes. So now this is a bit difficult because there are many possible reaction pathways. So to enable this, you have first to get the CO2 absorbed and activated, and then CO2 has to break in different molecules, as we mentioned. This is highly simplified, but you have CO from CO2, you have CO, and then CO has to couple to each other, and then you can make C2 products. The reality is that this is more complicated and not even fully understood. Why is this difficult too is because these different reaction pathways, they share similar thermodynamics. You see here the voltages versus the reversible hydrogen electrode of the different reactions. So within a few hundreds of millivolts, you have similar reactions. And also importantly, these reactions require a different number of protons and electrons to proceed. So you see here, to make complex molecules, you need lots of protons and electrons transfer steps versus the hydrogen evolution reaction, which is your main competitor here. So you want to promote these reactions selectively as opposed to this competing reaction. And I also like to show this graph from one of my ex-colleagues, one who shows using graph theory, how convoluted the reaction pathways can be, starting even from CO, which is simpler, how different products are related through different reaction pathways. And you can learn more about these works here through these references. So how people has, tried to improve the selectivity to this process. So the first thing that we learned, actually, thanks to Ori, he was one of the pioneers in this technology of CO2 electrolysis years ago in the 80s, is that depending on the metal catalyst that you use, you can have different selectivities. Okay, so there are metals that are very good to make hydrogen, there are metals that are very selective to make CO, others to formate, and others to make hydrocarbons. You can see here in this plot adapted from Hori's work how different metals promote, in this case, formic acid or formate, others promote CO. What's interesting here is that only there is one metal that can make hydrocarbons in an efficient way. So copper can make methane, can make ethylene, can make ethanol, lots of products. So it's difficult to get selectivity there. And thanks to the work of many smart people, and especially to the group of Norskov and others, now this can be understood and rationalized by how the electronic properties of your metals interact with the adsorbates, and this then proxies. We have proxies to understand how we can tune selectivity based on this. Now, changing the material might not be efficient because you have many reaction intermediates. So what people also try to do is just to design more sophisticated catalysts, like alloying different metals, introducing defects, changing the structure of the metals and the catalysts, and overall changing materials from the atomic scale to the micro scale. Okay, and I'll show later how this can be useful. And also, recently, more and more, we're learning how important it is to tune the more macroscopic properties of these reaction interfaces, so to tune mass transport and to control this through reactor and electrode engineering. And this is a very good summary of the progress for C2 chemicals, actually, for CO2 electrolysis that was published a few years ago. Now, you'll see a lot of these graphs today in today's presentation. So I like to look back to see how was the field looking like in 2014, when I particularly started working on this in the University of Toronto in the science group. So lots of groups started working on this area more and more through that time. And I would like to summarize the Faraday efficiency, the partial current, and energy efficiency, and the lifetime back then. So back then, there were already very interesting initial papers showing that we could be kind of selective to ethylene, like around 40% selectivity. But one of the important points is that the current densities were very low. So they were very impractical to achieve viability. They couldn't never overcome the capex cost required to implement this technology. The energy efficiency was very low. And the lifetime was, in some cases, not even considered, and not even considered now, actually, in some reports. So it's very important to mention this. I like to highlight one important thing, which is I mentioned how materials engineering could be used to design catalysts that are better and that offer more selectivity and more performance. But looking back, it's clear that qualitative leaps in applied performance were achieved by changes in device and device concept. So from the use of fundamental electrochemical cells, H cells, back in the 2010s, where the current densities were low, through the implementation of flow cells that enable higher currents and higher energy efficiencies, and eventually to the implementation of zero-gap membrane electrode assemblies, very similar to the kind of reactors that are used for AEM water electrolysis. So here you have a path to scalability as well and energy efficiency. One challenge also related to the catalyst design is that when you design a catalyst, you hope you have the perfect material with the perfect atoms, perfect coordination, perfect valence. But sadly for us, it's not so straightforward, because when you put your electrode in the electrolyzer, contact with electrolyte, and you apply a potential, very rapidly, in most cases, these electrodes and these catalysts change a lot. So not only they change in morphology, they change in composition. You can see here some beautiful examples using 3D electron tomography, but there are many others. And thanks to the group of many groups, but especially in Europe, I like to highlight the work of Beatriz Roldan and Rafaela Bonsanti, who did lots of work and is still doing lots of work to understand these transformations. We can now have more clarity on what we mean when we design a catalyst. We actually are making a pre-catalyst and then transforms during operation. And it's important to consider this when we design these materials. It's difficult to design of these electrodes, okay? Now, connected to this, I will also like to highlight progress from starting from 2014 up to now, that was achieved not through changes in the catalyst, but through changes in the reaction environment. So in all of these cases, you'll see like using the same electrode based on copper spatter on a hydrophobic support, a gas efficient electrode based on PTFE. Some works have achieved really important improvements. First, in selectivity at relevant reaction rates, here by enabling operation in alkaline environments, and we'll see now later that this also had some side effects. How using them further modifications of the environment, we could extend the selectivities to much higher current densities, comparable in some cases with even proton exchange and membrane water electrolysis. And this was achieved through the coating of catalysts with a particular type of polymer, naphthalene, that allowed for the extended availability of CO2 over the surface. And how more recently, using similar approaches, we could contribute solving one of the problems in the field of CO2 electrolysis, which is the very limited carbon utilization. And we will learn more about that in a bit. Okay, but the summary here is that, okay, designing fancy catalyst is important, but the reaction environment is also very important. And now, in the coming years, thanks to progress across the world in many groups, we are in a much more, better position where we have seen advances in selectivity reaching up to 80%, more current densities that are very promising, even above the ampere per square centimeter scale. Energy efficiency jumped from sub-optimal values to 20%. Is still far from targets and still far from competing, like sister benchmark technologies such as water electrolysis, but this is a good advance. And some progress also in stability, okay? And this is exciting, but also this reminds us that there are challenges ahead. I also like to highlight that some of these technologies are trying to be commercialized. So I like to highlight one example that that started at the University of Toronto in the Carbon X Prize contest in 2017, where there was a challenge to scale up the technology, demonstrate the technology that could convert and capture and convert 1 ton of CO2 per day. So this is based on CO2 electrolysis, and this resulted in the creation of a startup, Search Systems. You can learn more about this and other commercial endeavors in this paper that I don't have time to comment. But this was a very, very beautiful scale-up experiment, and actually coupled to a power plant in Alberta, in Canada. That it was very fun. So now, one of the challenges that I'm running bad on time. So yes, quickly, I presented some promising landscape for performance, but then there is also some very important challenge. So the use of alkaline environments and the fact that during water electrolysis and during CO2 electrolysis, you are also creating locally OH groups. So you are creating always hydroxyls here. this promotes the conversion. I mean, it's the same approach that is used for CO2 capture that Anna mentioned before. So this converts CO2 into carbonates. Okay, this is a downhill reaction, and this means that most of the CO2 that you put in the system are actually converted into carbonates. Only 5% back in the day was converted into the molecules of interest, and this has profound implications when it comes to the process. Okay, you can see here now combining all of the metrics where we were and what the target. Importantly, too, is to mention that I mentioned that some progress was made in individual performance metrics, but what often happens is that when you improve one metric, the other goes down. So we need progress not in individual metrics, but a holistic approach simultaneously in many different performance metrics. Okay. Going back to the carbon utilization, this is very important because when you consider the full process, it turns out that if you don't convert your CO2 into the target product, then you need to separate the CO2 that's converted from the carbonates. So you need to separate recycle the catholites, the anolytes, and you need to, well, do lots of downstream product separation, and this has lots of cost. You could see here the energy intensity versus the amount of CO2 that's lost into carbonates. So in gray, you could see the energy intensity of the CO2 electrolysis itself, and in this purple and blue colors, you could see the energy intensity that's required for separation. That's in most cases is higher than the energy intensity of the CO2 process itself. To overcome this, there are different strategies that have been proposed. So the use of bipolar membranes, operation in acid, and tandem electrolysis, among others. You can learn more about this in this paper published a few years ago. So, well, just to summarize this paper, I showed in a previous slide, but in this paper, just by controlling the reaction environment, we were able to demonstrate operation in acid media, increasing carbon utilization with moderate Faraday efficiencies, but showing that there is also a path to achieving higher carbon utilization in the field. I don't have time maybe to go through this, so let me close by saying that it's important to consider the full process in CO2 electrolysis. So integration with capture, also downstream. So everything is connected. So when you consider in this study, we were considering, okay, what's the cost and the global warming intensity of the different parts of the process. You can see from the upstream, you have some carbon negativity and you have some cost. From the core, you almost use electricity, so you have carbon positivity. So you're you're generating a carbon footprint, and also in the downstream. So only when you combine all of these in the right way, you have prospects to achieving ethylene in this case more expensive than typical fossil fuel ethylene. That's obviously the case, but that has some prospects for carbon negativity or carbon zero. So this is challenging to consider all the carbon emissions through this process and to see when the process is viable. So just to close, to summarize, this is what I believe is important to think about in the future of CO2 electrolysis. So we need more work on membranes and integration. We need also not to forget the coupled reaction at the anode. So we need tailored anodes and alternative, and other reactions in some cases could offer a path to higher energy efficiencies. Also new reactor concepts I've shown, like most of the biggest leaps in performance came through with the hand of different device concepts. And also demonstrate integration and scale, because until we scale things up, we don't know what will be wrong too. Also, these processes should be scalable, ideally not relying on critical raw materials or like forever chemicals such as fluorinated compounds. And yeah, I'd like also to thank our group. So this is a recent picture of a group in ICFO. We are located very close to Rovira, Virgili, a bit norther. So we are in Barcelona, in Castelldefels, in the south of Barcelona. And thank you all for your attention.
Thank you, Francisco, for your presentation and deep insight in the potential of electrochemical technologies for CO2 reduction. Let's proceed now with the next speaker. Walter Leiner is director at the Max Planck Institute for Chemical Engineering Conversion in Mannheim, under Ruhr, and holds the chair of chemical technology and petrochemistry in Aachen University, Germany. Walter Leiner has been active in the field of catalytic conversion of carbon dioxide since the early 90s, and he's recognized as a leading scientist in the field. The research efforts of his team have been recognized with several distinctions, including nomination among the top 3 innovations of the German Presidential Future Award in 2019 and the European Inventor Award in 2020 for an academic industrial collaboration to use CO2 as a raw material for polymer production. Please, Walter, the floor is yours.
Thank you very much, Anna, for the introduction, and thanks for being part of this exciting event. Now you could say everything has been said, but not by everyone. So I will try to bring in maybe some additional aspects on CO2 as energy carrier and feedstock. The framework has been set perfectly already by some of the previous speakers. Today, fuels and chemicals are closely connected in the petrochemical value chain, mainly based on crude oil, almost exclusively based on crude oil as the basis, with the largest portion going to fuels, but a very large portion also going to chemicals. And that is increasing because we have increasing humanity with increasing needs. While on the fuel side, of course, we also have alternatives like direct electrification. And we know that this is not a sustainable trajectory because the carbon that goes in here comes out as CO2 as the end. But what is very obvious is here that we use two things of the crude oil, the energy content and the carbon and hydrogen content, the material content. So it is an energy carrier and a feedstock at the same time. What is a possibility to work on the carbon balance of this process, as we have heard in many of the previous talks, is to bring in what is called green hydrogen. I will show it red because it brings in the energy, and the carbon taken from non-fossil resources. In particular today, we talk about CO2. And that could be funneled in, and the rest of this tree-like value chain remain the same as it is today, which has, of course, great advantages because that uses the existing assets and is, of course, of great importance. And so that is certainly an option. But we know that CO2 is not our only challenge. The production of chemicals in many ways exceeds planetary boundaries, not only on CO2, but also on other aspects. So what we also should consider is that we funnel these feedstocks in at several stages of this value chain to not only substitute the value chain that we have today, the same products and processes and process schemes, but that we use innovation to bring up better synthetic pathways, better processes, and maybe even better products that deliver better function than today to move into a sustainable future, not just by substituting, but by improving. And I would like to just highlight two of the important factors here. One is on the fuels, and many previous speakers have mentioned the Fischer-Tropsch process. And I'm actually very happy because I'm sitting here in my office at the very place where the Fischer-Tropsch process was discovered 100 years ago. And in May this year, we will celebrate the 100 years anniversary of the Fischer-Tropsch process here in Mülheim an der Ruhr in Germany, where it was discovered by Franz Fischer and Hans Tropsch many years ago. And I actually have here some original samples. So these are original Fischer-Tropsch samples made by these two gentlemen about 100 years ago. So what's new? What can we do beyond the traditional Fischer-Tropsch process, which arguably is incredibly important, in particular for aviation fuels and for fuels in general? But maybe we can improve it. And so the Fischer-Tropsch process is aiming at hydrocarbons as diesel or kerosene replacement. And in particular for kerosene, there's nothing else than hydrocarbon that we can see in the foreseeable futures. But for other applications, the combination, the molecular composition of the product could be actually an open design parameter, because as we change the feedstocks, we may also envisage to change the output. And in a design project, together with colleagues from combustion engineering at the Cluster of Excellence, the Fuel Science Center at Aachen University, we identified a mixture of hydrocarbons and long-chain alcohols as very interesting potential targets, because the use of such a mixture brings down the particulate emission and in the after-treatment systems also the NOx emission very significantly. It has a similar energy density. It can be used with similar or sometimes even improved energy conversion. It's retrofitting, it obeys with existing fleet compatibilities, bringing in these alcohols, but at the same time, it delivers additional benefits on the emission profile of the combustion engine. So we had to come up with a design of an innovative process to make such mixtures directly from syngas obtained from the renewable resources. And what we did is we combined the Fischer-Tropsch process with another syngas reaction, hydroformylation, in an innovative way to fully integrate these two steps. And this was not only done on paper, actually we made these fuels and they were tested in engines of existing fleet-compatible vans to demonstrate that this is really an option. And a full life cycle analysis executed by my colleague André Bardo at ETH Zurich showed that the orange line here is a battery-driven van, heavy-duty vehicle with a range of over 500 kilometers. The black line is conventional diesel, and the blue and the yellow lines are the hybrid fuels, depending. The blue is based on CO2, the green is based on biomass. And what you can probably see is that the best would be to use a combination of both, because biomass is limited in the availability. CO2 needs more energy to make the product. So combining these two feedstocks actually provides the optimum balance. So looking at Fischer-Tropsch fuels, they will happen. We've seen it, but there is also potential still to actually improve it. Now, the second big molecule that has been discussed already is methanol. Methanol is considered as one of the key targets to link energy and chemistry in the future, because it can be also upgraded to a fuel, or it can be used directly as a fuel, in particular in the shipping industry, but it also offers many ways to go into the chemical production. And it was advertised by Nobel Prize laureate George Olah in his book Beyond Oil and Gas. And again, maybe as a historical reminiscence here, Fritz Asinger at RWTH Aachen, already in the early 80s, he wrote a book, Methanol as the Main Chemistry and Energy Raw Material. And again, I have a copy of this book here lying on my desk, because he was the predecessor of my chair in Aachen 2 generations ago, already highlighting the importance of methanol as a potential key link between the energy and the chemistry sectors. And we see again many projects around the world, not only in Europe. China is very active. Carbon Recycling International, a company that started in Iceland, now is building projects in China. And also China has its own technology that they are developing, still not at the scale of the fossil resource, but maybe that's not even necessary, because maybe the economy of scale works differently in a renewable future because of availability of feedstocks and energy. We are collaborating with our institute very closely here with the steel mining industry company ThyssenKrupp, which, if I look out of my window, I can see their steel mines about 20-25 kilometers away from here, using the off gases of the steel mine directly for chemical production, and in particular, methanol is one of the targets. So again, the question is, what can we do beyond making methanol and substitute it today into various applications that we know already? What if we think ahead? How would the future potentially look like? And for that, let me just highlight that we have a very good fundamental understanding after many years and decades of fundamental research on the mechanism of these reactions. And this is absolutely fantastic. It's mind-blowing for the copper zinc oxide, aluminum oxide, the ICI catalyst that Anna already mentioned earlier. What the level of fundamental atomistic and molecular understanding is, how these catalysts operate, from many, many works. I just mentioned here my colleague Robert Schlögl, who has contributed to this a lot. And there are also other catalysts, molecular catalysts that work in solution, that have been recently discovered also to be able to take CO2 and hydrogen to methanol. I don't want to go into detail of these mechanistic pictures. Just take it that these are not sketches. These are not drawings. These are models that are based on a broad amount of experimental data, plus computational and theory and computational chemistry, to provide us stable and robust models that are able to reflect what's going on And now what we want to use this is to predict other reactions that could be based on that. And an interesting fact here is that although these are two very different catalysts operating under very different conditions, some of the key intermediates and of the key steps are actually very, very analogous, if not identical. But what we do now is we take this knowledge in order to use hydrogen and CO2 as building blocks in a kind of retrosynthetic analysis. So nobody on this planet, except for some crazy chemists, wants to have molecules and wants to make molecules. We want to have services and functions. So people need function that is delivered by the chemicals that we made, as coatings, as fragrances, as solvents, as agrochemicals to ensure nutrition, and of course also as fuels, as materials. So what we do is, we as chemists are the only group in the world that can connect the function with the molecular structure, and then go back and say, if we know these are the molecular functions that we want, how can we make them starting from CO and hydrogen in the beginning? And in all these structures, the green comes from CO2, the red comes from the hydrogen. And these are some reactions that have been discovered. Some of them are older, but some of them have been discovered in the last 10 to 15 years. And recently, together with Paul Anastas and Julie Zimmerman at the University of Yale, we've kind of suggested that based on CO2, you can also come up with a tree, like the petrochemical tree, to make all these kind of products. And the QR code here leads you directly to this paper. So with this, I would like to conclude already, to catch up a little bit with the time that we have. Yes, we have this knowledge, we can do that. And now it's time to bring this into the market. And the drivers are, of course, the technologies that are already mature, like Fischer-Tropsch methanol. But then we can think ahead and say, okay, this is how we shape a sustainable future by not just doing exactly the same as today on the basis of renewables, but that we can do better than we did in the past. And to hand over the knowledge from science to business, it's also important to think about the potential here for startup companies, because for the first time in a long history, there is a good case for creating a startup company in a niche and then grow in the chemical business, which on the petrochemical side was almost impossible due to the requirements of the economy of scale. Now there is a new world ahead of us. And so we are also supporting startup companies with an infrastructure located in Aachen in collaboration here with our Max Planck Institute, following the motto of the Max Planck Society, insight must precede application, which does not mean we can only do things that we understand, but means that we should think ahead and have ideas and then bring them into application. And for those who are actually starting in this realm in their startup business or do research, I like to remind you of Nelson Mandela's quote, "It always seems impossible until it's actually done." Thank you very much indeed, and I hope to see many of you in May here in Mülheim for the celebration of 100 years of Fischer-Tropsch. And if you still want to present something, the call of papers has been already closed, but I would be happy to receive any interest by email if there is still interest to participate actively, and otherwise you're happy to register, and we look forward to hosting and welcoming you here in Mülheim later this year.
Thank you very much, Professor Leiner, for your contribution and this proposing of a new way to see the problems, no, in specifically the CO2 transformation possibilities in this way. So let's move now to the final expert presentation. Last but not least, let me introduce Peter Buni, as Director of Sustainability and Technology at OCO Technology. Peter has been working on carbon mineralization for over 20 years, and with OCO, he has worked with business around the world to develop carbon mineralization solutions. Please, Peter, the floor is yours.
Thank you, Anna Maria, and good morning, good afternoon, good evening, wherever you're watching in the world. My aim in this presentation is to really sort of emphasize the potential of carbon mineralization. I think it's probably fair to say that it's perhaps maybe an under-recognised opportunity. Certainly in conferences and seminars that I've previously attended, there hasn't been perhaps the emphasis on this that perhaps I would have liked. So today that is my objective. So what I'd like to do, if this presentation will work, excuse me, there we go. Start off by just giving you a basic overview of carbon mineralization. And then I'd like to just look at some of the different types of technology in detail. And I'm going to present these as a series of case studies rather than talk just about the theory, because there's some fantastic work going on. And obviously I'm going to include OCO technology in that because it's a project very close to my heart. So as a kind of sort of an overview for this, carbon mineralization, I've essentially broken it down into three primary categories. Firstly, enhanced rock weathering, enhanced curing, so this is using construction materials to capture carbon, and then also carbon mineralization using wastes. And construction materials and wastes often go hand in hand. So there's some work going on, and OCO is one of those, who are taking waste materials, treating them with carbon dioxide and valorizing them as new construction materials that can go back into the supply chain as substitutes for natural materials. Now, we're trying to mention as many businesses and projects as I possibly can. Obviously, there's not time to talk about them all. So if you're listening and I've missed you, don't be disappointed. Just send me a message and I'll make sure you're included on a future presentation. If we try and break that down in a bit more detail, there's two basic methods that can be used to achieve mineralization. In situ mineralization is where you effectively have a multiple step in achieving the conversion of CO2 into carbonates. So this is where CO2 is dissolved into water, and it's pumped underground into a reactive rock formation, and the CO2 reacts with the mineral to form carbonate. Ex situ is where the process happens above ground. So in the case of rock, it will be mined, it will be crushed and processed, and then combined with CO2. Ex situ also applies to the use of waste and construction materials as well. In terms of the reaction itself, this can either be direct or indirect. So direct will be where the CO2 gas interfaces with the reactive medium without an intermediate step. So CO2 is contacted with the reactive material in the presence of water, and the CO2 is converted into carbonate. An indirect process is whereby the reactive element is extracted from the material first, so maybe with an acid, for example, and then is then combined with the CO2. So first of all, we want to take a look at mineralization in wastes. So it's a delightfully simple concept. You take a reactive waste, something that contains reactive calcium or reactive magnesium, and many wastes arising from thermal processes. So these would be cement, steel manufacture, energy from waste, anything that generally involves heat. It has the potential to produce a reactive waste material through calcination. So it's being heated, the CO2 present is being liberated, leaving behind a reactive material that we can harness. So we add water and we add some carbon dioxide, and we can put that CO2 back into that material. Just like to talk a little bit about some of the positives and the challenges involved in doing that. So I've mentioned that wastes are often very highly reactive. Some wastes can combine with up to 30% of their own weight in carbon dioxide. The beauty of this also is that the fact that very often they don't require any pre-processing. They're often fine-grained materials, so they are naturally in a very highly reactive form. Also, in terms of the carbon capture, generally speaking, the baseline is virtually zero. These materials will often be sent to landfill, so they're going to be sealed up in the geosphere with very little interaction with the atmosphere. So there may be some very, very long-term weathering of those materials and removals associated, but in the sort of our lifetime, the sort of the 100-year horizon that's often talked about in terms of carbon removals, there's actually very little is going to happen. So it means that any benefits, any carbon that is captured using this technique is totally additional. There's also the ability to valorize these materials as new products as well. So by diverting them away from landfill, treating them, we can then produce new construction products, which also has the double benefit of saving natural resources. Of course, there's some challenges involved in doing this. One of the big ones, and was mentioned earlier on, is regulation. Now, regulation obviously there for a good reason, particularly when we talk about construction materials. But it can sometimes be quite difficult to navigate your way through the various pieces of regulation that exist. And often we have a habit of creating additional regulation rather than consolidating and replacing the old ones. So it can actually become more and more complicated. In Europe, we have end of waste. So we do have the ability to be able to take waste and valorize them and put them back into the supply chain. But it's somewhat interpreted differently in different territories. So it's not necessarily a given that, having achieved it in the UK, you can then do the same in Germany, because whilst the Waste Framework Directive does give some guidance in this regard, as I mentioned, territories interpret this differently, and it's at different levels of development around the world. So Japan, for example, doesn't currently have an end of waste. So it can be quite challenging to penetrate new markets using these kinds of technology. There's also a degree of negative perception as well around waste. Thankfully, that is changing. When I started work in this sector 20 years ago, waste-derived products in particular had certain negative connotations with them. And it's good to see that now those attitudes are changing significantly, and people are regarding recycled materials as just as good as, if not better than, natural materials. The other challenge that has to be considered is that wastes, of course, aren't made to a specification. So there is variations in their physical and chemical properties, both in terms of time and in terms of geography. So you can get very different performance in those materials. So any process that you're attempting to use to valorize them has to take account for this. And ultimately, it's dependent upon the availability of biogenic CO2. So this diagram just really illustrates that whole concept. So you can take waste materials together with CO2 that's derived from industrial processes. You can put them together, you can valorize the material, and that gives you a resource that can then go back into the construction cycle. So my example for this, of course, will be OCO technology, who I've worked with for a number of years. We have 3 plants operational in the UK. Effectively, what we do is we take industrial thermal residues, predominantly from energy from waste. We treat those with carbon dioxide, and we produce an aggregate that can be used in applications like concrete and asphalt. And this picture here shows our facility in Leeds in the north of England. And the inset in the top left shows you a picture of one of the reaction vessels that we use for treating the waste with carbon dioxide. The carbon dioxide is biogenic. We currently take that from anaerobic digestion processes, but we have a project in collaboration with Mission Zero Technologies, who are developing a direct air capture process. So they have installed a pilot plant at our site, and that is due to become operational later on this year. So we're quite excited about the opportunities here. In terms of capacity, we process around about 200,000 tonnes of waste per year. And in terms of our carbon capture ability, that's around anywhere between 20 and 30,000 tonnes per year. This is what the process looks like. So effectively, if we start from the top left, we start off with a fine-grained reactive waste material that's brought to our facility by truck. And we process, for each site will process typically between 5 and 10 different materials from different sources. So we blend those materials together. So we can try and even out those potential variations in the waste. That material is then treated with water and carbon dioxide. In a second step, additional reagents are added, and then the mixture is then put through a pelletizing drum to form a rounded aggregate that you can see in the bottom right. This just shows you some photographs of a pilot project that we have together with our partners in Japan, Kobelco Eco Solutions. And the beauty of this system is it can be directly coupled to a flue stack. So we can take low purity CO2 and use it directly in our process with minimal gas processing. Typically, we're operating at concentrations of sub 10% here. In terms of global activity, so we've got a number of projects in Europe, Australia, United States, and of course Japan, together with Kobelco. But the one I really want to highlight today, and I know that a number of people who are collaborating on this project are in the audience, is our project together with Repsol in Bilbao in Spain. So together we formed a joint venture company called Biscay Eco Aggregates, or BIA. And we are building a facility that's due to become operational hopefully early part of next year. So construction has begun, and that will be taking residues from the local area in northern Spain, treating them with CO2 and producing an eco aggregate. The next technology I'd like to talk a bit about is enhanced curing, or capture of CO2 in construction materials. And I think the positives definitely outweigh the challenges on this one, because it's quite relatively easy to retrofit this technology. There's huge market potential, and there is the potential, there's a double benefit, as well as using CO2, there is also the potential with many of these technologies to reduce cement usage. So there's a double benefit. In terms of challenges, yes, of course, there could be regulatory constraints, particularly if we are trying to use waste materials in the process. And again, we've obviously got the consider the availability of biogenic CO2. The first example I'd just like to talk about is Carbon Cure. Now, they've been they're extremely successful. They have hundreds of facilities operational in America, and they've now started to make inroads into Europe as well, and they may well be active elsewhere. So their process basically is they retrofit a carbon dioxide dosing system to existing concrete plants. And essentially their technology involves dosing a measured amount of carbon dioxide into the mixing vessel as the concrete is being produced. The CO2 reacts with the cement, which is reactive with CO2, and forms tiny particles of limestone. This helps to enhance the strength of the cement, which means that the cement content can then be reduced. So there's a double benefit. The CO2 is captured in the concrete and the cement content can be lowered and still achieve the required strength performance. Another good example is Carbicrete. So Carbicrete are essentially producing masonry units, blocks, but instead of using cement, they are using steel slag. So instantly, huge reduction in the carbon footprint of producing these units. But then the units are then cured in a pressurized vessel containing CO2, and the CO2 reacts with the slag to form a carbonate cement that binds it together. So achieving the same performance as a conventional concrete block, but with a carbon neutral, almost carbon negative footprint. Other organisations using a similar process include Concreate or Orbix with their Carbstone products, very much the same, using slag cements and CO2 to produce carbonate cements. Neustark are another good example, who are making a lot of impact in Europe in particular. So their model is to take construction and demolition wastes. So when a building reaches end of life, it's demolished. The building is broken up, crushed up into small particles, and typically reused. If it's made from concrete, concrete of course contains cement, which is highly reactive with CO2. So their model is to take the construction and demolition waste, add CO2 to it, and produce a carbonated aggregate product that can then go back into the supply chain. Moving on from construction materials, we'll have a look at enhanced weathering. So again, this is one that is gaining a lot of traction around the world. So essentially it involves taking volcanic rock and scattering it on agricultural land. This material will naturally react with CO2. So materials like olivine or basalt, magnesium silicates, calcium silicates will readily react with CO2 in the atmosphere, but of course it's a relatively slow process on a geological timescale. So by helping Mother Nature, by taking the material, crushing it into fine particles, we're essentially accelerating that reaction. So as water falls from the atmosphere, it's absorbing CO2, that's contacting the fine-grained material that's been spread on the ground and turning it into carbonate. Ultimately, that carbonate is washed into the oceans, where it's said it can also help with acidification. Positives and challenges associated with this, well, the removal potential is enormous. There's also widespread deposits of these materials around the globe, and they can have huge reactive capacity. I mentioned olivine, which is really the rising star, can react in a 1-to-1 ratio with CO2, so that's its own weight in carbon dioxide. And the material can also enhance soil properties, so it can act as a natural fertilizer. Challenges, of course, the material isn't in a form that it can be readily converted. So first thing we need to do is need to pulverize the rocks into a relatively fine powder. And there's obviously things to consider there in terms of potential impacts of extraction and scaling up that extraction. And also need to consider the compatibility of the rock type with the soil chemistry. So first example I'd like to talk about is green sand, and their concept is delightfully simple. Basically, they are promoting the use of olivine, which is a magnesium silicate rock, and essentially they are just saying, why not use olivine in place of other materials, particularly for decorative purposes, for pathways or gardens. It's quite a pretty looking material, so now got that nice greenish color to it. So by getting people to use more and more of this and spreading it around, it's just acting as carbon sinks. The next one I'd like to talk about is heirloom. Now, I came across this a few days ago, and I was kind of captivated by this concept. So essentially, they are taking limestone, crushing it into a fine powder, and then heating it in an electric kiln powered by renewable energy. By doing that, they calcine it, so they liberate the CO2, leaving behind calcium oxide. That is spread out on hundreds, if not thousands, of metal trays that you can see in the photograph on the right. And that is just allowed to naturally absorb carbon dioxide, converting the calcium oxide back into calcium carbonate. That material then goes back into the kiln, is heated up, the CO2 is released, the CO2 is captured, and then it is permanently stored underground. And the process just keeps on going round and round and round as a cycle. Lastly, I'd just like to talk about the potential for carbon mineralization, which was the whole point of this presentation. Now, figures vary enormously, and you can go to different sources and they'll give you very different numbers. But I think these are, taking sort of a middle ground on this. So if we look at enhanced rock weathering, these values here are in gigatons of CO2 per year. Enhanced rock weathering has the potential to capture as much as 4 gigatons of CO2 annually. Waste materials can contribute, this is actually towards the lower end of the scale, 2.9 gigatons. I've seen numbers as high as 9 gigatons potentially. And then lastly, construction materials. Humanity's appetite for concrete is enormous. So construction materials offer the potential for up to 16 gigatons of CO2 annually. And that figure is taken from an article that was recently published in Science magazine, and I was asked to review on behalf of New Scientist. So I do encourage you to go and have a look at this. But yes, based upon looking at the arisings of industrial waste around the globe, the potential is enormous. And that's the end of my presentation. So thank you all for listening, and look forward to any questions.
Okay, thank you. Thank you, Peter, for this presentation, showing us the projects about this valorization of CO2 in construction materials. So now we are a bit late, but I think we can go for one question each of the panel experts. And then I think if you are asked to be please brief in your answers, to keep as much as possible, not too late. So let's go for Diana, please. I would like to ask you, what is the difference between fossil, biogenic, or direct air capture CO2 in terms of availability and in terms of costs?
Okay, the CO2 from the air is the most available, but also is the most expensive to capture as it is less concentrated. We have 400 ppm more or less of CO2 in the air. The CO2 from fossil fuels is cheaper to capture if the source is concentrated, and the availability is acceptable, but has the problem that will be banned from 2041 onwards. The regulation will be banned. So the biogenic CO2 capture is the solution, can be as cheap as fossil CO2 capture, but the availability is the problem that we need to face. No? Some concentrated sources are available, but not in sufficient quantity for the capacity of an industrial e-fuel plant.
Okay, thank you. So about the electroreduction of CO2, Francisco, what are the most pressing challenges to bring this CO2 electroreduction to real viability? We have seen one example already, but it's just a pilot plan. So what do you think?
So, yeah, well, I think focusing more on reliability, scalability, and stability is very important, and also connected to what Walter was saying, a very good point. So to which point these economies need to be scaled to benefit from economies of scale benefits, and how is the investment scenario changed compared to the technology? Because people, I mean, investors, venture capitalists, they don't like to invest on hardware so much or on these expensive technologies. So this is something to keep in mind as well, I think.
Okay, thank you. So, and Walter, we have seen that CO2 can be a feedstock for carbon-based fuels and also for chemicals. So what are the differences and the similarity between these two areas? So on the system levels and scientifically?
Yes, thank you very much. I mean, fuels and chemicals are always connected through the basic bond breaking and bond formation processes that are going on to make these final products at the end. This is the same today in petrochemistry. It was the same when it was based on coal. It was the same when it was based at some stage entirely on biomass in the old days. Now we look at CO2 as the feedstock, as one of the carbon feedstocks. So we need the same scientific tools, in particular in catalysis, to make this happen. And on a systems level, of course, fuels are always high volume, low cost, and chemicals very often low costs, low volumes and high costs. So they also complement each other in that sense. Fischer-Tropsch does not only produce fuels, there is a lot of other things that you can make out, and maybe that also can balance the economics. If not everything is targeted to make only kerosene, which is very hard. Maybe 60–70% of the carbon that goes in, you can make kerosene for the aviation. What do you do with the rest? Make something that is of high value.
Thanks for your view. And Peter, you mentioned many times the rules, no, the regulation. So how do you see the regulatory position changing with respect to using waste?
I think it's going to change quite substantially in the years to come. As I mentioned, it's in the time that I've been working in the industry. There's been a lot of change, but I don't think it's happening quite as quickly as it needs to. The good news is that there's more pressure coming from companies. There's the desire to use waste-derived materials, recycled materials. So I think the barrier in the way really is that very often the regulators of who are controlling the how we use waste and how we use materials are perhaps maybe a bit resistant to change, and I think that's understandable because of the need to ensure the performance of construction materials is maintained. There also needs to be more harmonisation as well. As I mentioned, there's different interpretations in different parts of the world as to how we drive the circular economy. So it would be good to see a bit more sort of joined up thinking in that regard.
Okay, thank you, you all for your contribution and discussion. I think it's time for the closing, and I just will highlight briefly some of the points discussed here. From the talk of Diana Cano, the conclusion is that we need to combine different technologies. So, but also those powered not only by biofuels, and according to their talk, also synthetic fuels are part of the solution in the transport decarbonization. Francisco explained us about CO2 electrolysis, but he stressed that the focus is needed in the holistic improvement of the metrics that are needed to maximize techno-economic and environmental viability from a full process perspective, including CO2 capture and downstream. And Walter Leiner, he presented this new way to revisit the chemistry and the transformation of CO2 to design new synthetic pathways, new processes, and even new products to deliver services and functions for the welfare of the humanity. And that is important to strive for innovation rather than for merely substitution in the transition to renewable energy chemistry interface operating within the planetary boundaries. And finally, Peter Guti has presented many possibilities of the valorization of CO2 in the mineralization way, but for the building and the construction area. So I think he also make a panoramic of what can be done with the family of carbonates. So now to close, I want to express my gratitude to the speakers, of course, for sharing your expertise and your perspectives at this point, at this critical point of CO2 transformation. I think that it helped us very much to understand the CO2 transformation technologies, also to Anastasios Perimenis for this overview of the CO2 activities and projects. And of course, the organizer, Repsol Foundation, and CO2 Value for all the technical staff for all the dissemination of this webinar. And also, I want, before ending, to also thank our technical staff at the University of Rovira, Virgili, who Jordi is the one who allow us to be there and no technical problems. And also to extend the thank to all the people registered and that joined us today. I think the massive attendance of you here is indicative of the interest and the importance of addressing the CO2 transformation through innovative solutions. And let's try all to include in our professional and personal life the reflections and the knowledge that we have shared today to work together for a greener use of the planet resources and to let the planet as better as possible for future generations. Thank you once again and goodbye.